In this question, we're told that in a seaside town, one tourist attraction, which is the whale watching boat trip, the owner claims that on afternoon trips, which each have a duration of 4 hours, there have been an average of 2.4 whale sightings per trip. A rival business doubts this claim and sends some employees to monitor whale sightings on 60 afternoon trips. The results are shown in the table below. So we've got some data for the number of sightings and the number of trips. The number of whale sightings per trip is modeled by a Poisson distribution. The first thing we're asked to do is to test the owner's claim at the 10% significance level and to show our working, including the expected frequencies, the test statistic, and the critical value, and state your hypotheses clearly. Okay, so let's make a start. As always, we'll start by defining the hypotheses. The null hypothesis is that the owner is correct and that X follows a Poisson distribution of 2.4 is a good fit, is a good model to use to describe the number of sightings. Alternate hypothesis is that this distribution is not a good fit or a good model. Because the question gave us the parameter 2.4, we have to use 2.4. Omitting 2.4 from these hypotheses will mean we don't get any marks for them. Carrying on, we're doing a 10% level of significance, so I can say that alpha equals 0.1. Okay, let's get the expecteds. We already have some observes on the right-hand side, so I'm going to calculate the expecteds. And to calculate expecteds, it's going to be the probability with this model that we get an outcome of 0 multiplied by 60. The sample size here was 60. So the probability that x equals 0 times 60, probability x equals 1 times 60, probability x equals 2 times 60, etc. So the expected values that I get are 5.44, 13.06, 15.68, 12.54, 7.52, 3.61, 2.14. The reason I always want to start with the expected is because they will dictate if we need to do any combining, if any groups need to be merged together. We're looking for expecteds that are below 5. Any expecteds below 5 need to be combined. And here I can identify that these are the ones that need to be combined. So I will refer to this group as greater than or equal to 5, and its expected value is 5.75. Now, the corresponding observed values will need to be merged as well. So I'm just going to transfer all the observes over here. It's a bit easier for me to keep track of when it's all written together. So the observed for this new combined group is 4. Degrees of freedom, we have 6 groups and we subtract 1 because we knew the totals. We don't need to subtract another one. We did not estimate any parameter. We were given the 2.4. And we can use 5 to find the critical value. So our chi-squared score for 5 degrees of freedom and a 10% significance level says 9.236. Okay, so just quickly on a diagram, here's the critical region. Anything in the shaded region will mean we reject H0. Now we can do the hard work of finding our test statistic. Test statistic comes from the observed squared divided by the expected. Observed squared divided by the expected, and we'll do that all the way through for each of these corresponding values. After I've summed all of those pairs together, we'll subtract 60. Okay, and then into our calculator, and we get a test statistic of 5.9235. Well, this is less than the significance level. 5.9235 is over here on the left. It's not in the critical region. There is not enough evidence to reject H0. It is not significant. We write out our comparison and then we need our 2-part conclusion. First, just as I said, not enough evidence to reject H0. And next one in context. So we can say there is enough evidence that X follows a Poisson of 2.4 is actually going to be a good fit. It's going to be a good model for this data. In part B, we're told that during one of the trips, the only sighting was a single group of 8 whales. With reference to the model, the Poisson model that we've chosen, state given a reason how this sighting should have been recorded. Well, one of the things about the Poisson distribution is that the events occur singly, one at a time. So although there were 8 whales at once, it is only one sighting. So we wouldn't be able to count that as 8 sightings. That needs to be one sighting. So we need to make sure that we treat that as one single sighting. No matter how many whales, until they've dispersed, that's one singular sighting.